You are streaking past Jupiter at 30,000 kilometers per second when an invisible force yanks you toward the darkness. 10 seconds later, your field of vision is swallowed by a circular black shadow. This is no nightmare, but the first 10 seconds of falling into a black hole. Imagine, the spacecraft you're aboard has just completed a Saturn ring exploration mission and is preparing to return to Earth. Suddenly, the navigation system blares an ear-splitting alarm. All instrument panels flicker wildly, and the spacecraft veers uncontrollably off course, accelerating toward an utterly dark region. You glance out the porthole. The once distant starlight begins to warp, spreading like spilled watercolor paint, while the darkness ahead looms larger and larger, its edges glowing with an eerie orange-red halo. This is no ordinary celestial shadow, but the most terrifying gravitational trap in the universe, a black hole. Over the next 13 minutes, you will experience the most extreme physical processes known to humanity. Time, space, and even the very structure of your body will be completely rewritten. Many people mistakenly think a black hole is a pitch-black opening in space, but in reality, it is a celestial body formed by the collapse of a massive star at the end of its life. A star more than 20 times the mass of the Sun, having exhausted its fuel, will collapse violently inward, becoming infinitely dense with gravity so strong that not even light can escape. This is the true nature of a black hole. To put it into perspective, if Earth were compressed to the size of a marble, its density would be sufficient to form a black hole. Stellar mass black holes, the most common type in the universe, typically range from 10 to 100 times the mass of the Sun, yet may be no larger than a city in volume. You can think of a black hole as a super gravitational trap surrounded by an event horizon. Once you cross this boundary, no signal can ever be transmitted to the outside again. It is equivalent to disappearing completely from the universe. When you are 100,000 kilometers away from the event horizon, the black hole's tidal forces already start to take effect. Tidal forces are the pulling forces caused by gravitational differences, much like how the moon's gravity attracts Earth's seawater to form tides. But the strength of a black hole's tidal forces is 100 trillion times that of the moon. At this point, the gravitational pull on your head facing the black hole is thousands of times stronger than that on your feet. This immense gravitational difference stretches your body toward the black hole while compressing it sideways. Imagine being grabbed by the head and feet by an invisible pair of hands, pulled violently in opposite directions. Your arms, torso, and even cells are stretched gradually, eventually becoming a long, thin strand like spaghetti. This process is known in astronomy as tidal disruption, taking only a few dozen seconds. You would likely lose consciousness before the pain sets in, as your brain is instantly destroyed by these extreme stretching forces. The moment your body, or rather, your spaghetti-like matter, crosses the event horizon, something bizarre happens. According to Einstein's theory of general relativity, gravity warps time and space, and a black hole's gravity is powerful enough to slow time to a near standstill. From the perspective of an outside observer, your figure slows down gradually at the edge of the event horizon, reddens, and finally freezes there forever, never disappearing. But in your own perception, time flows normally. Only the surrounding scene becomes extremely strange. You will notice that the light originally traveling forward begins to bend backward. Light emitted by stars behind you circles the black hole once before entering your eyes, allowing you to see your own back simultaneously. Even more astonishingly, you may witness every scene since the birth of the universe. Because the black hole's gravity warps space-time, converging light from both the past and the future here, you are like standing in a river of time, able to see all the scenery upstream and downstream. After crossing the event horizon, you will discover a terrifying truth. Space is no longer three-dimensional, but has become a one-way corridor. No matter which direction you fly, you will ultimately plummet toward the black hole's core, the singularity, like sliding down a slide with no exit, unable to stop descending. At this point, your speed is already close to the speed of light, yet the black hole's gravity continues to accelerate you relentlessly. All matter around you is falling toward the core in the same manner. Most of this matter is gas and dust swallowed by the black hole. As they collide at high speeds, they emit intense X-rays. But due to the barrier of the event horizon, these rays cannot escape to the outside, leaving you surrounded by perpetual darkness, with only occasional flashes of extremely faint high-energy particle light. When you are 1,000 kilometers away from the singularity, the surrounding gravity becomes unimaginably strong. The singularity is the core of a black hole, infinitely small in volume and infinitely dense. Here, the curvature of space-time approaches infinity, and all known laws of physics completely break down. You will find that your body is no longer spaghetti-shaped, but has been compressed into elementary particles, protons, neutrons, electrons, and possibly even smaller quarks. Driven by gravity, these particles hurtle toward the singularity at nearly the speed of light. At this moment, you are no longer a human being, but have transformed into a cloud of energy and particles, merging into the black hole's core. To use an earthly analogy, it is like compressing Mount Everest into a grain of sand, then compressing that grain of sand into an infinitely tiny point, a density beyond human comprehension. During your fall toward the singularity, you will witness the most magnificent visual spectacle in the universe, the ultimate manifestation of the gravitational lensing effect. The black hole's gravity warps surrounding light into a circular ring known as the Einstein ring. Formed by light from distant galaxies that has circled the black hole once, it looks like a glowing donut. Even more fascinatingly, you will see the entire universe reflected in this ring. Every star and galaxy is warped into an arc, as if viewing the world in a convex mirror. Furthermore, due to the black hole's rotation, the ring appears asymmetrical, brighter on one side and dimmer on the other, like a spinning, colorful halo. This is perhaps the most beautiful yet terrifying sight in the universe, for you know that after beholding this scene, you will vanish completely. It is worth noting that your experience will differ drastically depending on the type of black hole you fall into. If you plunge into a stellar mass black hole 10 times the mass of the Sun, tidal forces will tear you apart shortly after crossing the event horizon. The entire process takes only about 10 seconds. But if you fall into the supermassive black hole at the center of the Milky Way, the scenario is vastly different. The black hole at the Milky Way's core is 4 million times the mass of the Sun, with an event horizon spanning 24 million kilometers in diameter. Thanks to its enormous mass, the tidal forces near the event horizon are relatively mild. You might fly inside the event horizon for hours, or even days, before being torn apart by tidal forces. During this time, you can freely admire the wonders inside the black hole until you finally crash into the singularity. It is like the difference between falling into a deep well and a shallow well. The walls of a shallow well are steep, causing you to hit the bottom quickly, while the walls of a deep well are gentler, allowing you to linger in midair for a longer time. After you merge completely into the black hole, a deeper question arises. Will your information vanish forever? According to the fundamental principles of quantum mechanics, information is conserved. It cannot be created out of nothing, nor can it be destroyed. Yet the existence of black holes seems to violate this principle. Once matter falls into a black hole, it can never escape, and the information it carries appears to be completely erased. This is the famous black hole information paradox, which has perplexed physicists for decades. The current mainstream view is that black holes are not entirely black. They slowly release energy and information through Hawking radiation. Although this process is extremely slow, a black hole with the mass of the Sun takes 10 to the power of 67 years to evaporate completely. Theoretically speaking, the information you carried when falling into the black hole will eventually return to the universe in some form. This means that even though your body is destroyed, your trace of existence will persist in the universe forever. When we imagine the scenario of falling into a black hole, we are forced to confront a harsh truth. In the face of the universe's extreme forces, humanity is utterly insignificant. The technology and civilization we take pride in are powerless against a black hole's gravity. The wealth, status, and honor we pursue throughout our lives become meaningless amid the warping of time and space. Yet it is precisely this insignificance that deepens our awe for the universe's grandeur. Although black holes are terrifying, they are also an integral part of cosmic evolution. They devour matter, yet release energy through Hawking radiation, participating in the universe's material cycles and energy exchanges. Like the phoenix rising from the ashes, black holes destroy old matter and may even nurture new celestial bodies. From this perspective, destruction and rebirth are the eternal themes of the universe. As part of the universe, humans are tiny, yet possess the ability to perceive and contemplate the cosmos. This in itself is a miracle. Some may ask, what practical significance is there in studying a seemingly impossible scenario like what happens when you fall into a black hole? The answer is that black holes are the most extreme physics laboratories in the universe, allowing us to observe physical phenomena that can never be simulated on Earth. By studying black holes, we can verify the correctness of general relativity, explore the unified laws of quantum mechanics and relativity, and even uncover the mysteries of the universe's origin. For example, the discovery of Hawking radiation transformed our understanding of black holes from objects that only take in, never give out, to entities with both input and output. The detection of gravitational waves allowed us to hear the sound of merging black holes for the first time. These studies not only advance the development of physics, but also bring us closer to the truth of the universe. Although the journey of falling into a black hole is terrifying, it reveals the universe's magic and grandeur. From the time warping at the event horizon to the breakdown of physics at the singularity, from the spaghettification caused by tidal forces to the information returned via Hawking radiation, every detail of black holes is filled with the unknown and the fascinating. The universe's mysteries, like black holes themselves, seem distant yet constantly draw us to explore further. Perhaps one day, human technology will advance enough to approach black holes without being swallowed. Perhaps we will find a way to traverse black holes. Perhaps we will discover that the other end of a black hole connects to another universe. But regardless of the outcome, the process of exploration is a reward in itself. If you have other questions about black holes or want to learn the secrets of other extreme celestial bodies in the universe, feel free to leave a comment below, like, and subscribe. Next time, let's find the edge of black holes together and explore more wonders of the universe.